To me, it's an amazing thought to think that gold and these quartz veins form from a fluid. In a previous film, I interviewed Professor Stephen Cox, who explained the origin of these gold-bearing fluids. If you would like to see that interview, just follow the links. Now, in this film, which is part 2 of that interview, Stephen explains the relationship between the quartz veins, faults, and earthquakes. And he starts off by explaining that some quartz veins grow in layers, each layer representing a separate growth episode. I asked Stephen, what's the best evidence for this?
The really compelling evidence is in the gold deposits themselves. So if we look at the fault-fill veins, all that quartz and gold which occurs within the fault zones themselves, often you see textural evidence for episodicity. You see bands of differently textured quartz, bands with sulfides in them. There's clearly a sort of cyclic pulsing going on. It's not just one event which has produced the gold. We have evidence at the large scale in the mine and down at small scale in the microscope that these fractures have episodically opened up and then they've been sealed by mineral deposition and have opened up again.
How many opening episodes do you think?
It's hard to estimate, but some of the vein textures suggest that many deposits may have up to thousands of cycles of failure and mineral sealing.
So you can actually see the layers in the veins and count them?
Yes, particularly in the extension veins adjacent to the fault zones. There are very fine, delicate structures we call crack seal bands. And in any individual vein, which may be perhaps 10 centimetres thick, you might find 1,000 or more of these crack seal events. And we think, though we can't prove it, that each crack seal event probably relates to a failure event on the fault zone which hosts that gold deposit.
So is this at the microscopic scale?
This is down at the sort of 100 micron type scale.
And yet it's quite common, especially in the bedding parallel veins in Bendigo, to see quite thick multiple layers of a centimetre each.
Yes, that's right. Bendigo, you see this crack sealing at different scales. So you might have these centimetre scale veins separated by little screens of wall rock. But in some of those centimetre wide so-called laminated veins, if you go into the microscope, you'll see hundreds and thousands of these little crack seal bands spaced maybe 50 to 100 microns apart.
To explain how layered veins formed, we need to go back a few steps and understand the source of the gold-bearing fluids.
Well, the source of the fluid is devolatilization reactions as rocks deep in the crust are metamorphosed, that is, cooked up. As the fluid comes out of the crystal structure of the various mineral grains, it will carry gold from those minerals in the solution. Plus, as the fluid migrates up through the crust, it also has a capacity to scavenge gold from the rocks through which it's passing.
But there's a change in the way the fluid moves as it rises above the more ductile crust.
Ore deposit geologists for many years have had a concept of fluid flow being very continuous, a steady state sort of process. In fact, that's probably not the way the entire crust behaves. In the deep crust, the rocks are very hot, and that actually makes them quite plastic. Although at the Earth's surface they're strong and brittle, when you heat rocks up to 500 or 600 degrees, they're very plastic, and they flow much like plasticine does on timescales of millions of years. In that regime, the rocks deform very plastically without really breaking and producing earthquakes. This plastic flow is steady and continuous. So we think in the deep crust, the regime where earthquakes aren't produced, which we call the aseismic regime, we think the fluid flow is continuous or quasi-continuous. But there's an interesting change occurs at shallower levels in the crust. At about 15 or so kilometres deep in the crust, the rocks are cool enough and strong enough that rather than flowing plastically, they tend to break episodically. And this process is the process which generates earthquakes. The plates are colliding, and as they're colliding, the stresses are built up. And when the stress imposed on the rock, or the force imposed on the rock, exceeds the strength of the rock, it suddenly breaks, and that produces an earthquake. So we think this process may actually generate episodic flow in the higher crust.
With each earthquake, fluids can move into a fault zone, allowing quartz and gold to precipitate as veins. But the formation of new veins has an interesting effect on the later fluid flow.
This deposition of quartz is very important because it destroys the permeability. And if you think of fluids coming up through a plastically deforming shear zone into a cooler zone where quartz is being deposited and destroying that permeability, what happens is you're basically putting a seal on that transport zone. It's like turning the tap off. And if you keep supplying fluid towards this area where the tap's turned off, what happens? The fluid pressure builds up.
After an earthquake, the new veins seal the fault zone so that fluid flow is again restricted. This allows fluid pressure to build up.
It's exactly the same as the tyre analogy on a car. When the tyre's flat, the car is lower down on the ground than it normally is. You apply air pressure to the tyre, the air pressure is actually lifting the car up. It's the same within a fault zone or a shear zone. Eventually the fluid pressure in that actively deforming shear zone can exceed the confining pressure, the rock pressure acting on it. And that will actually nucleate a failure event, which will actually fail or breach that sealed zone. That will allow the highly pressurised fluid, which was trapped beneath the seal, to suddenly escape up the earthquake rupture zone. There, it then percolates into various structures which give rise to the gold deposits.
Why are earthquakes important to this process?
Well, it's very interesting. We could produce a gold deposit with continuous flow, but when we have this episodic failure and sudden fluid flow events, and then tail off of flow and quiescence, that actually creates better opportunities for creating gold deposits. Simply because if you have a fluid pressure builds up prior to the earthquake, as soon as you have a failure event, the fluid rushes up the fault zone. As it does so, the pressure in that fluid drops dramatically. And we know that the solubility of quartz is very pressure dependent, so that helps dump the quartz out. But there are also pressure dependencies in the solubility of gold and the species that transport it, which means if we have a very sudden and large fluid pressure drop in that fluid as it courses through the fracture zone, that will help dump the gold out.
Yeah. So do you think is it more important to have a lot of small episodes of release of fluid, a lot of small earthquakes? Is that more favourable to form a gold deposit?
I don't think we really understand that issue yet. What we do know is that a lot of the gold deposits we see in Victoria and similar deposits around the world is that each deposit is located or associated with quite small displacement fault zones. For example, the Wattle Gully deposit. There, the maximum slip on that fault zone is about 50 metres. That's probably accumulated through maybe 1,000 or 2,000 magnitude 4 earthquakes. And the other interesting thing is that often these clusters of gold deposits are spatially associated with bigger faults, and maybe these are the faults which are the main shock structures. And the view we're starting to develop through studying many of these deposits and doing some modelling work is that the big faults may act as the deeper level fluid conduits. And you have a main shock on that. The fluid rushes up that main shock rupture, which has high permeability, high porosity. It then gets distributed out into smaller faults, like the branches on a river again, but in maybe the delta type environment, we've got distributaries.
Is it more favourable to have the fluid dispersed into the smaller fracture networks rather than stay in the big shear zone?
It very, very much depends on the sort of reaction you want, or what is your favourite reaction to scavenge the gold out of the deposit. If you just want to get the gold out through purely a fluid pressure drop, you would like that fluid pressure drop to be really large, and you then want to be on the main shock structures, the big faults. But if you need some chemical fluid rock interaction, which for the Victorian deposits we seem to need, you want to be in a smaller structure where the fluid can actually discharge into the carbon-bearing wall rocks and react with them and produce species such as methane, which actually help scavenge the gold.
So it's not enough just to have a gold-bearing fluid. You need some chemical process to draw the gold out of solution.
That's absolutely right. There's two processes which you need to make a gold deposit. One is the physical process to generate fracture permeability to get the fluid to the site. Then at the site where the fluid is flowing, you need the chemistry to be right. And often that will involve wall rocks which are appropriately reactive, which set up the reactions which help scavenge the gold from that fluid.
Well, of course, there's miners' folklore going back 150 years in Victoria that some black shales are very favourable for gold deposition.
Yes, these black shales seem to be very important. They're black because they're quite rich in carbon.
So there's some truth to this then?
I think there's a lot of truth in it. And those guys knew what they were doing. They were very good observers and they saw the spatial association. We think now we understand some of that association. And one model we have is that the fluids that are coming up these fault zones discharge from the faults, react with those carbon-rich fluids, produce methane, and then when you have a major rupture event, some of those fluids are drawn back into the fracture system and mix And there's a redox reaction or oxidation reduction reaction goes on, which helps that fluid deposit its gold.
In many mines, it's common to see a vertical structure. The main lode or reef is nearly vertical. And yet the veins to one side are usually horizontal. Why is this so?
That's an interesting question and a very important one. The fault fill lodes are filling steeply inclined faults, which have slipped parallel with the fault surface like that. The extension veins off to the side have a different mechanism of formation. They form parallel to the plane of the maximum stress or force and perpendicular to the plane of the minimum force acting on the rock. And in Central Victoria, when these deposits formed, that minimum force or stress was oriented vertically, so they're formed perpendicular to that. They actually tell us a lot about the orientation of the stress field during these deposits.
So the individual crystals in the vein, in the horizontal vein, can grow most easily in that vertical direction.
That's right, because the fracture is actually opening in a vertical direction like that. The crystals tend to grow at a high angle to the fracture wall. But there's a very important concept here as well, and that is it says those steeply inclined faults are not particularly favourably oriented relative to the regional stress field. And we know from our rock mechanics studies and experiments that to actually get one of these steeply inclined faults to slip, you need extremely high fluid pressures. In fact, the fluid pressures have to exceed the vertical stress. And that again tells us we've got not just high fluid pressures, but to achieve that we need very high fluid flows.
So if there were no hydrothermal fluids interacting with the fault may not have much displacement or any.
It would never be activated at all.
So that's a really important and interesting point, isn't it? That there's this dynamic interplay between deformation and fluid pressure.
Yeah. Well, it's actually more amazing than that. There's this coupling between deformation, fluid pressure and the chemical processes going. They're all fully coupled, and we need to produce a gold deposit. We actually need all these things to work together to produce the right scenario. And if they don't work together, we don't get the gold deposit.
Often when we see these horizontal extension veins, say in the footwall of the main steeply dipping lode, they appear to be actually isolated from the main reef. So is that implying that there's some inherent porosity of the wall rock allowing the fluids to permeate through them?
Yeah, the fact that we see the quartz and the gold and various other minerals in those isolated veins does really tell us the fluid has percolated through the rock. And what we find in high fluid pressure environments, although the rock intrinsically has low porosity, low permeability, the high fluid pressure can actually act on that rock to actually crack the grains and allow the fluid to work its way out there. And the veins actually grow where the fluid pressure exceeds that minimum vertical stress acting on the rock. And wherever that situation occurs, bang, we'll start forming these veins. So often, say at Bendigo, you find these isolated veins in big sandstone layers.
So it's a very opportunistic fluid, isn't it?
Absolutely. The important concept is most of the breaking or failure process is fluid driven. The stress controls the orientation of the structures, but it's the fluid which generates its own permeability. It basically munches its way through the crust to go where it needs to go to drop its pressure.